Good afternoon. There is on Monday, as far as I know, there's midterm 2. You know your locations, obviously. They are posted on the web. And I got here a note from the Bioengineering Honor Society that they have a Chem 1A midterm review session tomorrow. And the session will be from 10 a.m. to 12 p.m. and 2060 Valley Life Science Building, VLSB. Tomorrow morning, 10 to 12, 2060 VLSB, okay? Go there. If you can turn it down a tiny little bit only a tiny little bit, please. Okay, now I have a little echo on my voice. The midterm will be not cumulative. It will be just from what we had from Monday when you had the midterm until today. This will be covered in the midterm 2. The final will be cumulative. All right, so today we're going to do a little bit of a review. I don't know how useful this is, but it's desired by you, that's why I do it. And we talked the last time in lecture 18, that was the last lecture, we talked about the simple gas laws. And Boyle, when he took a break from his suffocation experiments, if I could have your attention, please. He found out that the volume of a gas is proportional over a constant divided by P, or the volume times the pressure of a gas. An ideal gas is a constant. That was Boyle's law. And then we had Charles' law. Charles, he was the first one who flew in a balloon filled with hydrogen. He's seen that the volume and the temperature is proportional. Okay, and with this Charles' law, he said, if I plot the volume against the temperature of an ideal gas, and he experimented this, and he got a line, oh my God, he got a line like this, a straight line, and that straight line goes to, approaches 0. For one gas, or for another gas, it always approaches 0. With this, he thought, okay, now I have a thermometer. If I have 0 volume, there must be an absolute temperature, 0 temperature. And with this, he got the idea of an absolute 0 temperature, because there can't be a negative volume, okay? So if the temperature would go further down, the volume had to become negative. It would go down here. And so this is Charles and Gay-Lussac. They defined this here, that V, the volume of a gas, is directly proportional to the temperature. And I've shown you this with the balloon that I put into nitrogen. If you could have boiled the water, put it in boiling water, it would have gotten even bigger, okay? But it's more difficult to do. And with this, we have a new temperature scale, the Kelvin scale. And this is the scale that you're going to be using. K is Kelvin, is the degrees in Celsius, plus 273.15. So the absolute 0 temperature, which it cannot be reached because there is no volume 0, okay? The absolute 0, because you have molecules, they have a volume by themselves already. The absolute 0 temperature would be minus 273.15 Celsius. So anytime you do any calculation, that's the temperature you need in Kelvin. So, and the third law was Avogadro's law, that the volume of an ideal gas is proportional to the number of particles you have. 1 mole of any gas at standard temperature and pressures, which is 1 atmosphere and 273.15 K, how much is it in Celsius? 0 Celsius. Standard temperature and pressure. This gas has 1 mole of any gas has 22.4 liters. Okay? Doesn't matter if it's hydrogen, helium, nitrogen, oxygen, any gas that behaves ideal has 22.4 liters, because the volume is proportional to the number of particles. And if you have a mole, you always have the same number of particles. Okay? So we combine these three to the ideal gas law. P times V equals N times R times T. And you have then also partial pressures, and this comes here. the mixture of gases, they act independently. So if you have one gas, let's see, you have 50% of helium and 50% of hydrogen, and they each have half an atmosphere, or one atmosphere, let's say one atmosphere. You add them together, you have 2 atmospheres in that mixture, okay? Because each has one atmosphere, so you have to add it up. That means the overall property is the sum of the individual properties in mixture of gases. They act independently. So they said that helium says, I'm still have an atmosphere, and the other one says, I'm still an atmosphere, and the other one says, I'm an atmosphere. You put them together, they are 2 atmospheres. Okay, so that's how we come to the partial pressure. If you have a gas mixture, you have partial pressures. And you have also the mole fraction that this occupies in your mixture. Let's see what else is there. We come to lecture 9. No, let's go through this quickly here one more time. P times V, important, pressure in atmospheres, volume in liters, N is the number of moles, R is the ideal gas constant. And now you will remember I defined an R0 and R infinity, that was the Rydberg constant, or Ry, whatever it is. But it's a different constant, a different R than the ideal gas constant. That's the Renault constant. And you can use it, depending on what you are calculating, in atmospheres, liter per Kelvin per mole, or in joules per Kelvin per mole, and then it's 8.314 compared to 0.08206. These numbers will be given to you. And the temperature is given in which scale? Kelvin scale. Absolute temperature in Kelvin. So if I give you Celsius, you need to recalculate it to Kelvin. Sometimes you don't, but that's the problem. So we talked about so this, I ask you that question. I need you to show me that you were here. I'm going to ask you that question again. And I have an ideal gas in a balloon, and we heat this from 100 to, the balloon is 1 liter, and we heat it from 100 to 200 degrees at 1 atmosphere. So the pressure isn't changing, obviously. What is the final volume of the balloon? Is it smaller than 2 liters, or larger than 2 liters? I give you exactly 1 minute, and don't forget to click in. Since you know the question, we have in the discussion obviously now. Okay. One snuck in. Did you see that? Okay, excellent. All right, so that was clear. I was giving to you this to you at the end of the last lecture, and so the solution was V2, and I derived this for you and on the blackboard, actually. The only time I ever used chalk here. V2 equals T2 divided by T1 times V1. Okay, what's your T1? And T2 is 100 degrees and 200 degrees. So what T1 is 100 degrees, and if V2, that's what you want, that must be T2 must be 200 degrees. So some of you earlier said 200 divided by 100, that's 2, so it has to be twice the volume, which is of course wrong, because you need to use 373 Kelvin divided, 473 Kelvin divided by 373, and this is smaller than 2. With this, the volume is smaller than 2, as you so rightfully found out. So lecture 9, we talked about many electron systems and the shielding of inner orbitals. Okay, so and we looked at the orbitals themselves, and we looked at the 1s orbital, the 2s, the 3s, the 4s, and then we compared it in energy. If L equals 1, we have then the 2p, the 3p, and the 4p. So this was L equals 0, that's L equals 1. So you see, this is the energy scale here. Up here is 0, here is a very negative number, okay? So the 1s is the lowest, the 2s is lower than the 2p. So they're not degenerate, they have different levels of energy. And this comes because of the shielding effect, which I talk about in a minute. The 3s, these shield now the 3s, and the 3s is of course higher than the 2p, and the 3p is higher because it's shielded by all those here than the 3s, okay? And now we come to the 4s, which is shielded by those here, the 4s, and then we come to L equals 2, we come to the 3d, and the 3d is higher than the 4s, okay? Because of their shape. They are higher than the 4s. This is why if you look at the periodic table here, if you look at the third period, there's nothing in there. You see that up there? There's nothing in the third period here. That's the third period, because we are not filling. We could theoretically fill the d orbitals, but we are not filling them because the 4s is lower. The two 4s's are lower, 4s1 and 4s2. And now we're going to, that's the 4 here, and now we're going to fill in the 3ds. And how many d orbitals do we have? 5. A total of 10 electrons. That must be 10 elements here, if I calculate that right, okay? And this is 10 elements, okay? So the 3d is, due to the shielding, it is, the 4s is lower than the 3d, okay? So that's what I wrote here for you. And then you looked at the ionization energy. You know you can calculate the energy of a certain orbital, okay? N equals 1, n equals 2, n equals 3, so that's the main quantum number. We have done this many times. And that energy, is that negative or positive of the quantum level? Negative, has to have a negative sign in there, because we go from a very negative number, smaller and smaller till we get to 0, okay? In number smaller, okay? Till we get to 0, and with this we had the ionization energy. This is an energy that you need to bring to the system, because you need to pull off that electron from out of the orbital. You need to get it away from the nucleus, and this costs you energy. So you need to bring it, and the ionization energy is then positive. You see that? Okay? So the ionization energy of a one-electron system, we have discussed, this would be hydrogen or helium plus, is this, the nuclear charge squared, or the atomic number squared, divided by n is the level squared, the main quantum number, and so times the Rydberg constant. And so if we have, for example, helium, a hydrogen here, and helium plus, so it takes, now we, of course, you have a higher nuclear charge here in helium, but you have still 1 electron. It takes you about 4 times as much, because this is squared here. See, this is 2 here, this is squared, and this would be still 1, so it's 4 R's, okay? This would be that level if to get it totally ionized, and this 4 times this will be this here, okay? Now, if you say, if you helium 1s, that's a different story. You have 2 electrons now, and they shield each other. They try to get away from each other, but there's a certain shielding, okay? They shield the nuclear charge, and with this it will take you, this is where we were before, and this, now we have a many electron system. Now the effective charge is what counts. That's the charge that is really given to that electron, okay, that it sees from the nucleus. And since there's a shielding of these 1s, 1s shields the other one to some extent, it is now, it's not quite double, because it doesn't shield quite that good, but it is 2,372 kilojoules per mole to rip this electron, one of the 2 electrons, out to ionize helium-2 plus. Now, no, to ionize helium, I'm sorry. So if we have, for example, here, and this would be a helium atom, which is an in an excited state. The 1s got promoted, 1s stayed in the ground state level, and the other s got promoted to 2p1. Now let's look at the 2p1. Would you think it would be easier to remove that than the 1s1? Yeah, it would be easier to remove, exactly. So it actually is so well shielded, if it's in the p, that it behaves just if I would go from the second level for hydrogen and ionize an excited hydrogen electron, okay? So this is about shielding. So the effective charge can be calculated from the ionization energy, okay, and vice versa, of course. You measure the ionization energy, and then you calculate the effective charge. And then we talked about the Pauli principle, that no two electrons can have the same set of quantum numbers, okay? So if you have NL, M sub L is the same, then M sub S, the spin quantum number, if you have, has to be different. You have one upspin, one downspin. So you can, per orbital, how many electrons can you put in? 2, one upspin and one downspin, then you're done, okay? All right, so this is not a good combination here. This would be also not a good combination. So we're talking about which rule now? This is Hund's rule, and I gave you a little picture. I didn't dare to show it. There's a little picture in your handout if you look closely. So I talked about the bus where you're sitting in the bus, and you sit by yourself in the bus, and there are these rows, 2 rows, and somebody would walk in and just sit right next to you. That would be weird. It would be an absolute violation of Hund's rule. Yeah, okay. And so why doesn't the seats usually fill up by themselves, 1 in each seat, and then they start doubling up? Okay. I decided not to show this here because it's on the web. Right? Hund's rule, that means if you have orbitals of the same energy, you fill them with parallel spins first, and you fill the electrons in the lowest energy, always in the low. You start with the lowest energy. Now then we came to lecture 10. That is lecture 10, where we talked about electronic configurations and the Aufbau principle, which is now, you know, we went then and put all the electrons into the different orbitals. Nevertheless, we have seen that they are not, they are degenerated at the moment. They're all at the same level. This is just a scheme to build this up, okay? So you can build, and you can say then if you have unpaired electrons that there's magnetism, and where they are paired, there's no magnetism. So this is how we did this then till sodium, and we filled the S and the P's until we came to the 3s, and then, yeah, that's the same, the Hund's rule again. And then we talked about orbitals, orbital blocks. So this was the periodic system here, and if you look at this, we have this S block, where all the S1, S2 configuration have, S1, S2, 4S1, 4S2, 4S1, 5S1, and so on. So that's called the S block. This is called the P block, okay? And this is called the D block, where we start filling the D orbitals, starts in the 4th period. And then here you have the F orbitals filling after 57, after lanthanum. The F orbitals, what number are those? 4F. And these are the 5 Fs here. These are the lanthanides and the actinides. So what can you tell me about the behavior between sodium and potassium? Would it behave similar? Why would that behave similar? Same valence electrons, same valence electron configuration. The configuration for all these babies here from lithium to francium is S1, 1s1, 2s1, 3s1, 4s1, except hydrogen is really not a homologue. We call those homologues. They behave similarly within one group. So that what I wrote to you, homologue elements in a periodic group exhibit often similar chemical behavior. And now we're going to come to ionization energy and electron affinity. Ionization energy. Is this an energy that you need to put in the system or you get out of the system? Put in. What's the sign? Positive, exactly. So we ionize an atom, we rip off an electron, so we have to get it away from the influence of the nucleus, and we need energy, and we get that free electron, okay? So we have an ion then. Electron affinity is when electron is added to an atom, a neutral atom, and this is a process which is exo or endothermic. Exothermic. It gives off energy. What's the sign of the energy here? Negative, exactly. So I have given you here ionization energies and electron affinities. You see the ionization energies are all positive, very difficult to take off electrons here. And the electron affinity, it's very, obviously these are very electron affine, okay? They like to have electrons. We can explain this, for example, with, what's that called? Electronegativity. We could explain that. So let's look at the ionization energy again a little bit more. So we have the ionization energy is within each group, each period. As you increase the nuclear charge, the ionization energy increases again, okay? Once you have the period filled, you go to the next period, you start here again. So there's this trend that the ionization energy, there's a big difference here in the second period, and in the third period, not so pronounced in the fourth and the fifth and the sixth period. Of course, you have all these electrons around there, and it's not, they don't see that nuclear field as much anymore, so it's not that difficult to remove them. You see that the number itself also goes down. You see that? You're down here, radon. Where is it? Radon, radon, helium, deuterium, argon, radon. Radium here, so what do we have? What's this, titanium? No. Here's radon, okay? So in this period, it's much easier to remove because you have all these electrons here from those guys here. You have them shielding the nucleus. Then we talked about the successive ionization energy. That means you rip off one, you remove one electron, let's speak properly. You remove one electron, that takes a certain amount of energy. But now you have one electron less, but the nuclear charge is still the same. So the rest of the electrons are bound stronger because now one negative charge is away. And so the positive charge hasn't changed. So it's exerted much stronger onto the electrons, that charge. And so you need even more energy to take off a second electron. And you can see this goes from 580 to 1,815 kilojoules per mole. And if you remove a further one, the third one, you have the same effect. You need about, just for that one electron, you need more than 4 times, nearly 5 times the energy to remove that electron. And about 20 times the energy to remove the last one, okay? Because you have removed electrons, but the charge hasn't changed, the nuclear charge hasn't changed, so it hangs on much tighter to the rest of the electrons, all right? So the atomic radii increase within a group. If you go, they increase, they get larger. Of course they get larger, you're getting to the next period. You have all these electrons around, they're getting larger. But the phenomenon is they decrease within the period because as you add nuclear charge, it pulls in the electrons stronger, and this wins in this case. So you go from left to right, you decrease the atomic radius, and from top to bottom, you increase it. Remember that. What else do we have here? Okay, electronegativity. What is electronegativity? That would be the distribution of electrons, or the ability of one binding partner in a bond with another partner to pull the electrons away from that partner. There is the possibility that it can pull it totally away. Then we speak about ionization, okay? It ionizes that one, and the other one takes that electron, so it does is then an anion. You have a cation and an anion then. So if there's a very large electronegativity difference, then you have ionic bonding. If you have a not so large electronegativity difference, then you have some polarization. It pulls a little bit more into the direction of the more electronegative. You have a covalent bonding, but a polarized covalent bonding. Such bonds, would they have a magnetic momentum? No. What? Of course they would have a magnetic momentum. If it's a polarized, they would have a magnetic momentum, all right? because there's more negative charge on one atom than on the other. So with this, they would have a momentum. So what's the highest? This is a relative number to each other. They studied many compounds, and Pauling came up with this scheme. What's the highest, the most electronegative atom? Boron. And the least? Francium. Okay? This is the most electropositive. That's the most electronegative. And so with this, you know now that the electronegativity increases if you go from left to right within the period, if you go here. So which one would be more electronegative? Sulfur or chlorine? Excellent. Good. All right. So you go from left to right and decreases from top to bottom. Now what I just told you, the ionic bonding, you take the difference of the two electronegativities, and if you have, for example, sodium and chlorine, you can read it off your table if we give it to you. Sodium has 0.9 and chlorine has 3.2. Okay, so the difference 3.9 is 3.2 minus 0.9 is 2.1, so it's larger than 2. With this we say it's ionic. That means it has totally pulled the electron away from the sodium atom and forms a Cl minus and an Na plus ion. This is an ionic compound. Isn't it ionic? Okay. So the next thing is we have partly ionic. That means partly ionic or covalent polarized. Okay. Covalent polarized means you have hydrogen chloride, HCl. Hydrogen, chloride minus hydrogen is something 3.2 minus 2.2, so it's 1, okay? It's between 0.4 and 1, so that's partly ionic. That means it has a magnetic dipole, okay? Which also will have a magnetic momentum then, okay? So the dipole is, the electron density is more on the electronegative. You have the delta minus here, and this is more electropositive. So the electron density goes in this direction. So the dipole would go into that direction. And then you have the ideal covalent, which you only can have. You can have covalent bonding if the ideal covalent, if you have two of the same kinds bond to each other, Cl2, F2, H2, then they split the electrons right in the middle. None pulls anything. So that would be 0. But we talk about it already if it's smaller than 0.4. And so chlorine would be 3.2 minus 3.2 would be 0. The perfect covalent bonding. All right? Let's see what we have here. Okay, polar covalent bonded molecules like these here, these are all polar covalent, they display a dipole momentum. I need 3 arms and 4 hands. So now we're going to talk about Lewis structures. No, that's not right. So we have 3 different kinds of bonding. I'm going to review that one more time for you. We have covalent. The bond type, the difference in the electronegativity is around 0. It's covalent. Intermediate difference is polar covalent, okay? Or partly ionic, you also can say that, all right? And the electronegative difference is very large. You have ionic, the electron is really transferred over, okay? So you have ionic, polar covalent, and covalent. And then I already showed that polar covalent bonded molecules display a dipole moment. Now we go into the Lewis structures. And this is the first sort of bonding theory we came up with. Lewis came up before they knew about orbitals and so on. He came up with this theory, and it just works very nicely. That's the Lewis dot structures. So you look at the valence electrons, and you count how many valence electrons you have, and at every valence electron you use 1 dot, okay? And then when they bond, they try to fulfill either in the first period the duet rule, and in all other periods the octet rule. All right, so you have, for example, lithium has 2s1, okay, 1 electron, 1s electron, so you have 1 dot, 2 dots, and so on until you have neon. Neon would be the stable configuration, would be 2, 4, 6, 8 electrons, and argon would be in the next period. That would be sodium would have 1, and argon has 2, 4, 6, 8 octet rule, all right? So now we do the ionic bonding, what I just explained. You can do ionic bonding with Lewis structures. So you have lithium has 1, and fluorine has how many electrons? 3 electrons, or valence electrons? 7. So 1 and 7 will give 8. So this fluorine needs to get 8, and if this gives off the 1, it has the configuration of the one below of neon, actually. No, of helium, I'm sorry, of helium, okay? So this would take over that electron completely, and because of the difference in electronegativity, there is ionization, okay? This will be ionic bonding. So the fluoride minus fluoride ion and the lithium plus. And so they are attracted to each other through Coulomb interaction, Coulomb attraction, okay? So this would be 2, 4, 6, 8, fulfills the octet rule, and this fulfills the octet rule of helium. Actually, it fulfills the duet rule, okay? Now sodium does the same thing. The chlorine pulls the electron to make chloride, 2, 4, 6, 8, octet rule fulfilled. The sodium becomes positive, and now it's the neon configuration, okay, which is also octet rule. Remember, you can do it you can pull off 2 electrons. One chlorine pulls one off, and the other chlorine, you have 2 here, pulls the other off, so you have Mg2+, Mg2+ is magnesium, 2+, has neon configuration, okay? I pulled off 2 electrons, and the chlorine has become an octet, so you have 2 chlorines here, one here, and one here, okay? With this, you have the octet rule fulfilled. So covalent bonding is an equal sharing. You have, for example, we talked a little later about molecular orbitals. Hydrogen fulfills one hydrogen here, duet rule fulfilled. Cl2, 7 valence electrons, 7 here, bonds like this, 2, 4, 6, 8, 2, 4, 6, 8, octet rule fulfilled. HCl, okay? So this is, H is 2 here, and 2, 4, 6, 8 on the chlorine. Would it be polar or not polar? Polar, exactly, it is polar. And the momentum goes from the more electropositive to the more electronegative. That's this delta plus here and delta minus there, okay? Now, the octet rule here again is for oxygen. You know how to do this now. Oxygen is 2, 4, 6, 8. There's a double bond here, 2, 4, 6, 8. 2, 4, 6, 8 for nitrogen, triple bond, 2, 4, 6, 8, triple bond. How much has nitrogen? How many electrons, valence electron does nitrogen have? 5. 5 and 5 gives 10, okay? All right, 2, 4, 6, 8, 10. There you go. Carbon monoxide, for example, has this here. And you have carbon. Carbon has how many electrons? 4. And you get 1 each from the hydrogen to form that bond. So that would be, carbon would be 2, 4, 6, 8, octal rule fulfilled. Hydrogen would be 2, 2, 2, 2, duet rule fulfilled. You can also have free electron pairs, okay? NH3, 2, 4, 6, 8. And octet rule fulfilled, duet rule fulfilled. But when you get down in the third period, you can, and further down, you can get in trouble because you're running out of electrons necessarily. And so you have xenon tetrafluoride. Xenon is far down here. So you have, no, you don't run out of electrons. You have too many electrons, let's put it that way. Xenon has 2, 4, 6, 8, 10, 12. It's 12 electrons, so there's an exception. It's not 8, it's an exception of the octet rule. And we understand this a little later when we talk about the steric numbers. Boron trifluoride has, for example, also it's below the octet. I don't have enough electrons here to fulfill the octet rule. Possible. Boron trifluoride, 2, 4, 6, 8 on the fluorine, 2, 4, 6, 8 on the fluorine, 2, 4, 6, 8 on the fluorine, but 2, 4, 6 on the boron, below the octet rule. So formal charge is something which was important for you when we talk about resonance structures, when you have several possibilities to draw your Lewis structures, because actually these oscillating between these electrons are oscillating between the 2 or 3 structures that you can draw. And the rules for formal charge is that the formal charge is the number of valence electrons on the free atom minus the number of valence electrons of the atoms in the molecule. You assign lone pairs entirely to the atom. You share electrons equally between sharing atoms. You share them equally. And then the important part, atoms and molecules try to have formal charges as close to zero as possible. Okay, atoms and molecules to have formal charges as close to zero as possible. So if you, for example, have SO4, would there be a possibility that you could have a negative charge on the sulfur? Theoretically, there would. Okay, and I gave you an example. But there are two things that speak against that. So where would be the negative charge, on the sulfur or on the oxygen? On the oxygen. Okay, why would that be? More electronegativity. Excellent. Okay. So, and then you can't just wildly distribute the charges. You need to balance it. First of all, you need to balance it. But on the other hand, you need to have the least number of formal charges for your resonance structure. So negative formal charges, and we already did this, was with the most electronegative atoms. So then we come to lecture 14, where we talked about the valence shell electron pair repulsion model, the VSEPR. This gave us now the possibility to start binding in 3 dimensions. Okay? So we use the VSPR model, and we draw the Lewis structures for that molecule. That's the first step. You use any, if you have resonance structures, they have to be right, of course. You use any of the resonance structures, okay? Because any of them are true. Then you count each multiple bond as a single effective pair, all right? You count the electron groups around the central atom, determine the electronic shape, the electron shape, arrange the electron groups to minimize repulsion. Okay? So now, and then with this you determine the molecular shape from the position of the atom. So the steric number determines the geometry. So we talked about steric number linear. You have the steric number 2, okay? You have 2 bonds, steric number 2, that would be a linear molecule. If you have steric number 3, and I explained to you how to get this steric number, you have a trigonal planar molecule, so there is the possibility to have electrons here, here, here. Okay, so with this you could get this shape here, and what would that be, for example? Let's see, there would be a free electron pair in this case here. You would have funny shape, angular bend. Nevertheless, your steric number would be 3. Think about it. If you have one with a free electron pair and it's flat, then this is how it would be looking. If you have the steric number 4, you have a tetrahedron, and the tetrahedron has a bond angle of 109.5 degrees between each bonds here. So it points towards 4 directions. You can bind to 4 different things, or 4 things, so to speak. And now, if you only bind to 3 things, seem to be 3 similar things here, and you have 1 free electron pair, what's the bond angle? 107. Name me a molecule. NH3, okay. Now, we have even a more extreme case where we have 2 free electron pairs. 1 here and 1 there. With this, we have this angular bend, but we have steric number 4, okay? Steric number 4, and we have that these pairs here. And that would be, for example, what's the angle here? Name me a molecule. Water. Okay, let's have some. I'm sorry. That was the key word. All right, I don't have any chem quizzes. I'm talking without interruption, which is not good for me and not good for you either. Number 5, steric number 5, you have a trigonal bipyramid. Looks like this. Now, if you have a free electron pair here, you have something like funny shaped seesaw. You see that here? Seesaw. And if you have 2 free electron pairs, you can give even a T shape, all right? So you have, this one would be a free one, and this one would be a free. You have this funny T shape like this here, and you still have 90 degrees angles here. Octahedral, okay, steric number 6. You can have this here, an octahedron. Can have 1, 2, 3, 4, 5, 6 bonds here in space. Or you can have a free electron pair. You would have something like this, a square pyramid. There's your pyramid here, and there's the square on top. See that? Okay? And then if you have two free electron pairs, you could have a square plane. That's really strange. You have a planar molecule because one of them is here and the other one is here, the free electron pair. Okay. We always have to position the lone electrons to minimize the electron repulsion, okay, so that they are as far as possible away from each other, that there's not so much repulsion. So lecture 15, we talked about isomers, and they were structural isomers, isomers have the same molecular mass, but they can have, if they are structural isomers, they can be totally different molecules. They can have the same number of bonds. They must have the same number and same type of bonds and the same number and type of atoms. So this is C2OH6, okay? This is ethanol, and this would be dimethyl ether, same number, same molecular mass, everything, totally different compounds. These are structural isomers. And this is a very, very significant difference between them. They're essentially two totally different things. You can have more subtle or differences if you have stereoisomers. This, for example, is a C2H2Cl2. It can have each of them has one chlorine and one hydrogen on the carbon. So this is the trans configuration. And this would be the cis configuration. They're on the same side, they're across here. And this would have some small differences, but they are very, very subtle, these differences. Now, there would be, of course, a structural isomer of those here, or of this here, if we would put the chlorines both on the same carbon. Then you have a structure, very, very significant differences between this and that, all right? So that behaves very, very differently. So you could also then see if there's a magnetic momentum or a polarization. You can do that. So would that have a momentum here? No. That goes in this direction, that goes in that direction. That would cancel each other. Now this one goes in this direction, so this would have a momentum, would be the vector addition of these two vectors, would be a vector, which we can draw here, for example, would be this here, or this would have a momentum, this goes in this direction, this in this direction, so the vector addition would be that here, and with this would be the momentum. Then we had these funny isomers that are very important for our body. We had these stereoisomers, and they are also called enantiomers. A mixture of them is called a racemic mixture, a racemate. So they are essentially, they have no superimposable mirror images. They have a chiral center. Chiral center means it has in this case it has 4 different atoms on it, but a chiral atom and the chiral center means that it has 4 different things, 4 different groups around. And so this would be the L form, and this the D form. Our body usually only processes the L form. It uses L amino acids to make proteins, and chirality you can compare with your hands. They are non-superimposable mirror images, right? This is what a chiral molecule is. You have chiral hands, feet are chiral, and so if we look, for example, at this amino acid alanine, we look at this one here. So this carbon, is this chiral? Has 1, 2, 3, this must be hydrogen here, 3 hydrogen, no, okay? Is this here chiral? Has 1, 2, 3, something the same, must be also hydrogen. Is this chiral? Has 2 the same, also not chiral. Now this one has 1 hydrogen, has 1 carbon here, 1 carbon here. You could say, oh, it's not chiral, that's wrong. That's why I say 3 different things, okay? This is CH3, that's a CH3 group, and this is a CO2 group, this is a hydrogen, and this is an NH3 group. So would that be chiral? That's the chiral center, and that's the mirror image of that chiral center. You see that? The mirror image of that chiral center, all right? So what else did we have? Yeah, chiral, I say it again, chiral molecules have a central atom that bonds to 4 different groups. And we come now to the review of lecture 16, where we talked about bonding and anti-bonding molecular orbitals. This was molecular orbital theory, where we had constructive interference to a bonding molecular orbital sigma, that would be 1s and 1s, in phase bonding, out of phase anti-bonding, sigma star. The atomic orbital is here, the other atomic orbital is here. The bonding sigma is lower, and the anti-bonding sigma star is higher. And we have done this then with helium. We can determine then the bond order. Helium, what would be the bond order here? You have helium had 2 here and 2 here, 2s2, 1s2, 1s2. Now you go bonding, 2 here. First you fill 2 in here, and then you fill 2 in here. What's the bond order? 0, okay? No bonding. Helium-2 doesn't exist. We can do this now with lithium. Lithium would have a bond order. What would be the bond order? You don't forget that you have the 1s sigma and sigma bond also, okay? So, but they are lower in energy than this stuff here. So, and if I ask you a question, you will have a scheme, but don't forget to fill it in from the very bottom, okay? So you can't throw away electrons. So this, what would be the bond order of this? So there's 2 minus 0 divided by 2, bond order is 1. Bond order of beryllium? Does it exist? No. Yes, good. Here's bond order. Okay? So the stability of the molecular orbitals depend on the bond order. Okay, that is fine. Let's see what we have here. Aha. If we come to the p orbitals, you can have sigma bonding and pi bonding. How many overlap of 2 sigma if you have 3 p orbitals? They can overlap in 3 different ways, actually in 2 different ways. How do you get sigma bonds in p orbitals? Head to head. That's this baby here, okay? All right? So that would be the bonding and the anti-bonding. The more nodes you have, the higher in energy you are. Now you have side to side, you have get a p bonding and a p anti-bonding. So that would be the p z orbital. Which one is missing? The px, this one here. This one to this one would be the same. So you get 1 sigma and 2 pi's. So this is the same thing here. We did that already. See that? The sigmas and the pi's. And then we talked about the valence bond theory, and this is the valence bond theory. It uses hybridized atomic orbitals. So we use 1s and 1p to get ready to bind in a 180-degree angle. We use an sp hybrid. So if you have 1s and 1p, how many hybrid orbitals do we get? 2, okay? These are the 2 hybrid orbitals, 2 sp orbitals. Now, you see here, you can now accommodate steric number 2, 3, and 4. This would be an sp, this would be an sp2, and tetrahedra would be an sp3. And now we run out of shape because we have used all the s and the p orbitals, and so we now need to use the d orbitals. But first I want to ask you, and this is an important question, like all the questions that I ask you are important. So if you look at that carbon here, and what is the C2H4, okay, double bond here. How is the double bond made? The double bond made is, this is here, what's the hybridization on this here? sp2, okay? That forms that sigma bond here. And here you would have the hydrogen, and here you would have the hydrogen, here you have the hydrogen, here you have the hydrogen. How many sigma bonds do we have? 1, 2, 3, 4, 5 sigma bonds, okay? And how many pi bonds do we have? That's that pz orbital that overlaps to form that pi bond. That's this one here. So the question is, how many sigma bonds? 1, 2, 3, 4, 5 sigma bonds and 1 pi bond, okay? So the orbital hybridization, we go to the next period. We have steric number 5. We need to use now the d orbitals. So we have 1d, 3p, and 1s. So a dsp3 or sp3d, whatever you like. So with this you get trigonal bipyramidal, and this would be the orbital, and these are the examples. We had this earlier. And then you have d2 sp3. How many d orbitals do we have left here? 4, okay. They are still there, these 4, And in the lower, a little bit lower, are the hybridized ones then. And with this one, you have how many d orbitals left? 3. They are not hybridized. And with this, you get this here, and this would be a question I could ask, but I don't. And with this, I wish you good luck, and I see you on Monday, fresh to lecture, and on Monday evening is your midterm. Don't forget to do the homework, it's important. And don't do it in the last minute.